Hi, so today we'll be actually starting with some of the topics of the research methodology, right? And now let's get started. So firstly, let's have a look at the topics that we actually need to cover, right? So we have say chi-square tests, right? So chi-square tests actually have we have some notes, something like that, right? It's actually a statistical test which actually tests the differences between the expected outcomes and the actual outcomes, something like that. Then we are actually having some of the tests of the independence of the attributes, right? You might have heard about the problems where you have different attributes and you have the combination of two binary particular attributes, like someone is educated and someone is say having job, something like that, or say man and woman and so on, right? Literate, illiterate, these are the attributes, and when we actually combine those attributes we actually get some characteristics of a particular person, and we get combinations. So this is actually related to that. So then we are actually given with the say regression, right? Linear regression, like good fit, bad fit, and so on. So this is actually the part of the linear regression. These are coming into say research methodology as a subject also. And then we are actually with the ANOVA, which is called analysis of variance, right? It's also a statistical test which actually tests how much varying your data is, and we actually will learn a bit of it in detail, right? And then in the ANOVA we have two things. One is actually one-way ANOVA and another one is actually two-way ANOVA. So we have these particular things in our handsets, right? So starting up with chi-square test. This is actually not chi-square, this is actually chi-square test, right? So let's actually get started with that. Let's zoom in a bit. Okay, so chi-square test, you have say a particular graph of the probability, which is actually alpha, right? And then do you have the chi-square value, which is actually along the x-axis, right? When you actually get the value, say number of variables, right? K is actually a number of variables. So your graphs actually comes out to be something like this, and when you actually get the variables to be say around say 10, you will actually get a very steep kind of say curve, and you will have the normal distribution in between. So this is actually just a graph representing that. This particular region is actually H1, right? You might have heard of the normal distribution, that you have the confidence interval in which you actually want the results, and the interval which in which the result doesn't lie. So alpha is the particular value in which the result doesn't lie, but the 1 minus alpha is the region where the hypothesis result lies. So this is actually represented by H naught, and this is represented by H1. For example, say you are actually taking up the value of say alpha to be 0.1, so you mean that okay, so 10% will be the portion on left and right, that your region will be there. It means 10% of the region will actually contain the out of hypothesis values, right? Means whatever you have considered as a hypothesis, it will actually come out of that by 10% confidence, right? And 90% means rest other than that, it will be actually the region where the value will actually lie. So in chi-square test we use the chi-square distribution, and in the non-parametric test we will not use the parameters like mean, variance, proportion, etc. So basically, okay, so if we actually talk about the earlier tests, right, they were parametric tests, right? Parametric means that you actually consider some parameters. And what are parameters? Parameters means the actual values of variables of a particular population, like the mean, variance, and standard deviation. And we consider that the particular population is from a particular distribution following some of the parameters. But chi-square doesn't assume those particular parameters, and it's calculate irrespective of what the distribution is about the particular population. So this is actually a non-parametric test, right? Okay, so the chi-square with k degree of freedom is the distribution of the sum of square of k independent standard normal random variable, right? So we'll actually take say it has a k degree, means degree of freedom is actually k, if it's actually having k independent standard normal random variables. P-value is the area under density curve to the right of the value of the test statistic. Reject H naught if computed value chi-square is greater than the critical value. Okay, so you have this particular curve, right? You will actually get a particular critical value by looking at the particular tables, right? And so if the calculated value comes out to be greater than the means the chi-square value comes out to be greater than the particular critical value which you actually found from the table, then you will reject the null hypothesis. See, there are two concepts here: null hypothesis and alternative hypothesis. Null hypothesis is what you have assumed. Alternative hypothesis is the opposite of that. For example, you say that a particular population has a mean of say 24, right? Then your alternative hypothesis will be that the population mean is not 24. In a similar fashion, if you say the null hypothesis is that your population mean is less than or equal to 24, then the alternative hypothesis will become that the population mean is greater than 24. So if one comes out to be true, you have to reject another, right? And this is actually based on the values which you compute. First, you actually in the previous test also, like say we have p test and we have t test, right? If I actually give you a particular recap, so uh, p test was actually done when you have a large number of population, like say above 30, but you have a small number of population below 30, then you use t test, right? And then they're also used to calculate some particular value, right? And then check for the value from the critical value which you actually find from the normal distribution tables, right? Here also you will have a particular chi-square table, right? So what you will do is that you will actually just calculate this particular value and you will check against the critical value. If you will actually find the value to be greater or lesser, right, you will actually get the decision or take the decision accordingly. Here it is actually given, if it is actually greater than the particular critical value, it means that it's actually going towards this particular region, right, where there is a rejection region. Then you will actually reject the null hypothesis and you will accept the alternate hypothesis or the opposite case. So let x1 is the standard normal variate, and so we are actually taking a particular variate that's actually x1, and it's following normal distribution with the mean 0 and variance 1, right? Now we actually take the expectation of x to be 0 and variance of x to be 1, means expectation is nothing but the mean in the layman terms. Now we have theta 1 is actually x1 square, that is degree of freedom. Then you actually calculate the theta 2 with the x1 square plus x square, that is 2 degree of freedom, and theta 3 will be represented as x1 square plus x square plus x square, that is 3 degree of freedom. Now test the difference for of more than two properties is actually where you actually use a chi-square test. If you have to do the test of the independence of the attributes, then you actually do the chi-square test. And when you have to do the test for the goodness of a fit, then you use the chi-square test. So these are the three use cases where chi-square test is actually done. One, when you have to get the difference of two particular properties, right, or more than two properties, right, then you actually do the chi-square test. Properties are nothing but the variables, right? In your data set you have columns, and then you have the independence of attributes, right? So you have, as we actually talked about the attributes, so we'll actually get the independence among those attributes. Then we actually get the goodness of a fit, means how good your fit is particular in a particular scenario. Then you actually do the chi-square test. Okay, so first scenario where chi-square will be used is that test of the difference of more than two properties, right? When we have more than two properties, we do the test, right? A major political party wishes to test if the proportion of its supporters in three states are same or not, right? So okay, so if a particle actually wants to get that, okay, the proportion of supporters in the three states, they are actually getting examining their votes in particular three states, right? And they're wanting to test the proportions, right? Means how many of them are actually supporting them, how many of from the total population, and they want to see if the proportion is actually coming out to be same from all of the three states or not, right? The party conducts a survey of 1,000 people in each state and found that there are 300, 350 and 425 supporters in the sample in the surveyed states. So basically they actually got that there are a total of 300, 350 and 425 supporters in the samples, right, where they actually surveyed the particular states. Using these data, test if the true proportions are same or not, right? Okay, so see what's the question is about. Question is saying that you have actually done a survey of 1,000 people, right? In each state, means in each state you actually taken thousand people, right? Actual number of people were actually higher, not just 1,000, right? But among 1,000 only, you actually got 300, 350 and 425 which were supporters. Now with these statistical tests, you want to actually get to know that whether the true proportions of the actual population, means whatever the number of people live there, are actually the same or not. So h1 says that pi1 is equals to pi2 is equals to pi3. That's actually all the proportions are same. Then h1 is actually says that not all pi1 is actually equal to pi2 is equal to pi3, means not all are same, something is actually different, right? So in the state 1 you actually got the yes votes from the 1000, that's actually 300. In the state 2, 350, and state 3 is actually 425. In a similar fashion, you actually want to get the vote of no, you will actually subtract from 1000 because the total were 1000. So you actually got 700, 650, and 575, right? Now you will actually get the chi value, right? So how will you will actually get the chi-square value? This is actually the symbol chi, right? And you will actually calculate the c value. It means calculate the value. C actually means here is the critical value, right? This is how you will actually calculate the critical value, and you will actually test the particular value from the table against this, and then you will actually take the decision to either accept the null hypothesis or reject the null hypothesis, right? And this is the particular formula, that is Oij minus Eij and whole square of that and divided by Eij. O is actually the observed value, right? Observed value, right? Sorry, C for C actually means for the computed value, not the critical one. And the alpha, with the alpha you actually calculate the critical value, which is actually taken up from the table, right? So this is what you compute, so C, and this is what you actually get from the table, that's actually shown by alpha. Alpha is nothing but the interval in which the rejection region lies, like it here it was taken to be 0.1. Okay, so this is your Eij is actually expected value, and Oij is actually your observed value. This is the actual value which you see from the table, and this is the value which you expect to actually come. Now Oij is actually the observed frequency of the cell in the ith row and the jth column, and Eij is the expected frequency of the cell in the ith row and the jth column. Now Eij comes out to be corresponding row total. So how will you actually calculate this Eij? That is the expected value. So you actually do corresponding row total multiplied by corresponding column total divided by grand total. So that's actually your Eij, right? Means whatever the row was actually having a sum in total multiplied by whatever the column was actually having a sum in total, and divide by the total cells, total of all the cells. That's actually coming out to be Eij. Now you have chi-square follow the chi-square distribution with r minus 1 into c minus 1, a degree of freedom. Df actually stands for degree of freedom, right? So if you actually want to calculate the degree of freedom of a particular table when you have r rows and c columns, then the degree of freedom will come out to be r minus 1 into c minus 1. Means one will be subtracted from both, and both rows and column will be multiplied. And yeah, it actually follows the chi-square distribution. Like we have normal distribution and Gaussian distribution, we also have chi-square distribution, right? But it's actually different in case, so we will have a different table to look from in this particular case. Okay, now I have the particular this degree of freedom will be in particular case, right? Two conditions must hold for the same. That is, one is actually sample size must be greater than 50, right? In the p test and t test we used to have the condition with 30, right? Here the sample size must be actually greater than 50, and each cell have expected frequency is at least 5, right? So every cell's expected frequency must be greater than or equal to 5, right? Okay, and if not, if it's actually not the case, if it's actually not at least 5, it's actually lesser, then you have to actually merge with the previous cell. Later on we'll also have a look at the numerical, so don't worry. For now, let's just read what are the particular steps in the chi-square test, right? And now, as we have already read that if the computed value is actually greater than the critical value, it means it is actually lying in the rejection region. So it means that H naught or the null hypothesis will be rejected, and the alternative hypothesis will be accepted. So this is the wholesome process of chi-square test, that you will have some particular table like this, right? You will actually calculate the chi-square value with this, and this actually observed value you actually get directly from here. You will actually subtract all of those followed by the square of that particular difference divided by the particular expectation value which you actually calculated. And how you actually calculated the expectation value is actually the corresponding row total multiplied by corresponding column total divided by the total grand total. This is actually you will get the EIJ, and then you will actually get the chi-square value. After looking at the chi-square computed value, we'll actually check for it to be greater than the particular critical value. If yes, then it will be rejected and H1 will be accepted. And this is actually the wholesome process of chi-square test. Okay, so here is a numerical, right? So how we will actually do it exactly. So here we actually got that particular supporters in the state, right? In this particular table, so we have this particular supporter, right? So yes, no, right? State 1, state 2, state 3, and then we have total, right? Okay, so yes, so we have this O say 1 1, and then here O 1 2 and O 1 3. O means actually observed value, as we have already filled up the table. So these are the observed values, say 300, 350 and 425. And in the second column we have second row and first column, that's why O 2 1 and O 2 2 and O 2 3, right? We got the values, say 700, 650 and 575, right? In a similar fashion, right? So, and the expected value is also calculated for some of those, we actually calculated the E101, that is corresponding row total multiplied by corresponding column total and divided by this. How we actually got this corresponding row total is that we added all of these, right? We added all of these. How it actually come out to be 300 plus 350 comes out to be 650. 650 plus 425 comes out to be, say, 1075, right? So this is actually you get the observed values, say total, right? Observed value totals. And here we know that in each state 1000 were actually the total number of samples, right? For the people. So here the total comes out to be 1000, and divide by means it was actually corresponding divided by grand total. So how much total value is actually for the all. So here we actually got the 3 1000. That's actually come out to be, say, 3000. So this is your grand total, right? Means how many total observations were there in all. So you actually got the E11. In similar fashion, we'll actually calculate for E12, E13, E14, E15, E21, E22, E23, right? Similar fashion, we actually do all the corresponding row total multiplied by column total. That's 1000 divided by 3000. This is how you will actually calculate all the EIJ values, right? And then finally you actually do this particular XC, that is chi computed square, will be calculated for all. That is summation over all cells, means here we have 1 2 3 4 5 6 cells. So we'll actually do all of them, right? Expected value is actually calculated in this fashion. This is 358.33. Then these both will be subtracted, right? And then we will actually get a square of all those and divide by 358.33. This is how we will actually get the chi-square computed value for E11, right? And then we have the degree of freedom to be calculated. Now, okay, so why this degree of freedom is actually needed, right? We actually need this degree of freedom to actually get the critical value from the table, because the table here is actually something like that, that you have particular multiple columns, right, in which you are actually given the degree of freedom, and for those corresponding whatever your degree of freedom is, you will actually see the look at the value in that particular degree of freedom column only, right? And the row will be actually chosen by the alpha value which you are taking. Here I think we are taking 0.05. Yes, we are taking 0.05. That's actually a rejection region, means 5% reduction region, right? 5% confidence, right? Okay, so sorry, that's actually 95% confidence and 5% rejection region, right? So you will actually get the alpha value to be 0.05 and degree of freedom. So you will actually look at the row which is actually containing 0.05, and we actually look at the column which is actually containing the degree of freedom to be equal to 2, because here we have rows to be total of 2 and columns are actually 3, as we see in the table. 2 rows, 3 columns. 2 minus 1 comes out to be 1, 3 minus 1 comes out to be 2, so degree of freedom is actually 2. So we'll actually get the alpha 0.05 square value to be only seen from the table. That's actually 5.99, right? And then, and this is actually the significance, how much significance level is. So this is actually 5% level of significance, and here the computed value square is greater than the actual critical value. So it means that, okay, so what was the computed value? It comes out to be 34.93, and actual value, critical value is 5.99. So we see that we need to reject the null hypothesis and accept the alternate hypothesis. So it means that in reality, the actual proportion of the people supporting the parties was not equal in all the states. Whatever the values of these particular sample population may be any, but the actual region was actually not, actual proportion was actually not same for that. Okay, so we have actually seen that how the chi-square test is actually being calculated for a particular scenario and for a particular question, right? So let's actually proceed further. Yeah. So now we'll actually have a look at the test for the independence of attribute. This is actually the second condition where the chi-square test is evaluated for. First one is that when we have the particular previous scenario, right? So we actually have three scenarios in total, right? Test of the difference of more than two properties, right? Two properties actually being checked, or more than two properties are being checked for the difference, right? That's actually the first scenario, right? And the second scenario is actually the test of the independence of attributes, and the third one is actually the test of the goodness of it. So now we'll actually have a look at the test of independence of attributes, and here we will use a chi-square test, right? So we may be interested in knowing whether a new medicine is effective in controlling fever or not. So chi-square computed test means chi-square test will help us in dividing this in deciding this particular issue, right? Means whether a particular medicine is actually effective or not, right? Let's proceed with H naught, that the two attributes the two attributes new medicine and control of the fever are independent, right? Means we have two particular attributes here, right? One is actually that the medicine, right? Means whatever the new medicine is that, and second attribute is actually the controls fever or not, means whether it's actually able to control the fever or not. It means that the new medicine is not effective in controlling the fever, right? So now we have the attribute A is divided into R classes, say A1, A2, say to up to AR, and B is also divided into C classes, right? So there are different particular set of classes, right? So H naught says that A and B are independent, right? It is a particular case when you have, say, XC computed comes out to be, say, lesser than x alpha, that's actually x alpha square, means the critical, if we actually compute the particular chi value, it comes out to be lesser than the critical value, then it will mean that A and B are actually independent. But in the case when the x computed comes out to be greater than x alpha, then H1 will be accepted, and it will mean that A and B are not independent, right? Okay. Okay. So let's actually see. Uh, Two researchers adopted different sampling techniques while investigating the same group of customers to find the number of customers falling in different buying intelligence level. Okay, so we have the table as follows: that we have particular two researchers, right? It's actually the researcher column, right? And say number of customers in each particular level, right? So below average, then we have the average, then above average, and the genius, right? Means this is actually the intelligence level of this particular in the buying habit, right? Okay, so we have one category and two category, right? So below average are 86, average are 60, above average are 44, and genius are actually 10, right? In the similar fashion for the 2, 40, 33, 25, and 2 are there. So we'll actually do the total among this, among this, among this, among this, and here also, right? And the total there were 300 in all, right? So grand total value actually got already. Other two sampling techniques, so this actually I believe the two sampling techniques, right? Because say in the one sample you actually got this, right? Maybe from the different region. And in the second sample we actually got this particular distribution, right? So the question arises, or from the part from where null hypothesis will be developed, is that are the two sampling techniques of and the buying intelligence significantly independent, means we are actually checking for the independence of the attribute. So it means that we'll actually need to calculate the chi-square value, and we'll actually need to check for the say independence, right? According to this particular condition, whether if the computed value is coming out to be lesser than the critical value, it means that they are independent. If it's actually coming out to be greater than the critical value, it means they are not independent, right? And the significance level or alpha is coming out to be, or say given to be, say, 0.05, right? Okay, so let's go further. So here the two sampling techniques and the buying intelligence level are independent. Okay, so we got that. So we developed the null hypothesis to be that the sampling techniques and the buying intelligence are independent, right? These are the two attributes, right? So on the left side we actually saw that in the table we have the sampling techniques, right? Two particular sampling techniques were used, and in the column wise you were actually having the buying intelligence level. These were actually the four columns, right? So you want to actually get to know that whether this attribute and this attribute A and B are say independent or not. So chi-square formula will be again same, right? That's actually for all the cells. You actually get the difference between the observed ij value and the expected ij value and divide by and square of the that, and then that will be actually divided by the eij. So you already know that 011 is 86, 012 is 60, and 013 is something something something, and going up to say 200. And in a similar fashion, 021, that's actually observed or the actual value, right? How does E11 E12 come out to be? We remember the formula still, right? We remember here we have actually not shown that, but you remember what the formula was. That was actually the corresponding row total multiplied by the corresponding column total divided by grand total. So what is actually about that? If we're gonna calculate say E11, right, then the corresponding row total is 125, corresponding corresponding row total come out to be say 200, corresponding column total come out to be say 125, and divide by the grand total, that's actually 300. This is how we actually calculated 84, right? In a similar fashion here, row total will be 200 only, but the column total is 93 divided by 300, and we actually got one E12. In the similar fashion, you will fill up the particular table, right? Now what is required? We actually want to calculate the chi-square value, so that will actually in the similar fashion using this formula, that is this minus this square divided by 84, 62 minus 60 square divided by 62, or you can do 60 minus 62 square also, but the value will be same because it's actually just a square. In a similar fashion, we'll actually calculate all of those, right, and then we'll actually add up all of those, and then you will actually get the value of this chi-square. That's actually coming out to say 0.923. Now you actually want to know what's the critical value is, so that you can actually compare for the lesser or greater. So alpha value was given to be say I think 5% significance was actually given. Yes, 5% significance was interval. So you actually need two values to actually look from the chi-square distribution table. That is, you need alpha value means the significance value and the degree of freedom. Now how do you calculate the degree of freedom? That's actually r minus 1 multiplied by c minus 1. R here is actually the number of rows to be 2, C is actually the number of columns, that's actually 4. So 2 minus 1 is actually 1, 4 minus 1 is actually 3, so degree of freedom is actually 3. You will actually look into the third 3 degree of freedom column from the chi-square distribution table, and there from the table you will get to see that the value is actually 5.99, and the 5.99 is far greater than 0.923, and we know that if xc square is lesser than x alpha square, means chi alpha square, then those h naught will be accepted, and these two attributes are independent. This is actually the acceptance region. If it's actually coming out to be greater than that, greater than say alpha chi alpha square, then it's actually the rejection region, and both the attributes are not independent, right? In the previous scenario, the xc was actually far greater than the x alpha square value, or say we can say that xc square is greater than x alpha square, and that's why we were rejecting that thing, and the proportion was coming out to be not same, and then an alternate hypothesis was accepted, but here the null hypothesis is actually accepted. Now the third condition of the goodness of fit, right? Here we will also use the chi-square test, and let's see. So it enables us to find that if the deviation of the experiment from the theory is just by chance or due to inadequacy of the theory to fit the object data, right? So you actually propose some theory, right? You actually do the experiment where there is a deviation in the results of the experiment, and you want to test that whether the deviation is actually just by chance that it is actually deviating for this particular moment now, or there is inadequacy in the theory to fit the particular object data, means the theory is actually incomplete. You actually want to test that, right? So here comes the question. And company A had recently conducted aggressive ads campaign to maintain and possibly increase its share of market for fabric software, right? So this actually just a problem statement that recently a company has increased the advertisements, right? So that is actually can increase its chance in the market for the fabric software. Their main competent company, B, has 40% of the market, and A number of other competitors. Okay, competitors account for the remaining 15%, right? Okay, so this particular company who is actually selling fabric softeners as actually just increasing their ads into the TVs, right? So they have their competitor B, right, who's actually the 40% of the market, who's actually holding 40% of the market, and rest of all the competitors in the market, right, are actually 15%. To determine if the market share if the market share changes after the campaign, the market manager of A dictated the preference of random sample of 200 customers. 102 indicate the preference of the company A, and 32 for B. Okay, and remaining 16 for others. Can analysts infer that the customer preferences are changed? Okay, so these were the particular metrics, right? The main competitor are actually having 40% of the market, and the remaining were actually having a 15% of the market, right? So they actually did a survey, right, in which they actually take on up 200 customers and ask for the fabric softener which they would like, and they actually got that 50 means 102 customers were actually wanting say the particular say their product only, right? 102 were actually wanting their product only. And 82 were actually wanting the B product, right, which is actually their competitor. And the 16 were actually wanting some other product, right, which is actually out of the competition, right? So can an analyst who's actually collecting this data still infer that the ads actually helped or not, right? And we have to use a significance level of say 5% or say 0.05 value for this particular case, right? Okay, so this is an example of the good fit or not. So whether H naught is actually H naught is actually our null hypothesis, and it says that the fit is actually good, or the object data is drawn from the population having the specific distribution, and H means actually that the fit is not good, right? So we want to say that here the particular distribution, right, whatever the distribution is from where we are actually collecting the data of the ad preference is actually a representative or a good fit of the actual population with a specific distribution. This is actually our null hypothesis, and the other one is actually alternate hypothesis that this distribution of 82, 16, and 102 are actually not the representative of the actual population, and their actual preferences are different for the public, right? They want to see that. So we will actually calculate the XE square value again with the same formula, right? That's actually summation over all of the value minus expected value square divided by expected value, right? So observed frequency of the ith class, right? That's actually your OI minus EI, right? And then the expected value will be again the same, total frequency of the row, total frequency of the okay, so now here the expected value is actually a bit different, right? Here we are actually getting the percentages frequency, so the expected value formula is a bit different here. That's actually, if you are going to calculate for the ith class, then it will come out to be say total frequency of the ith class multiplied by the probability of that particular class. And the key, if there are k classes, then the degree of freedom will come out to be say k minus 1, right? Here we don't have say those particular cell kind of thing, right? We want to actually only calculate for the particular classes, right, and whether a particular class is actually there to be right or not, right? Okay, so we actually got that if we have k particular classes, then we have the degree of freedom to be say k minus 1. In the previous scenario it was row and column only, but here in the good fit is actually k minus 1, and the expected frequency or the EI is actually whatever the total frequency of the particular class, whatever the total frequency for your data is multiplied by the probability of that particular class. Okay, and here also the some similar consideration, right? Like the sample must be actually having a value of greater than 50, means 50 people or more must be or say 50 greater than 50 people must be considered for this particular case. Right here we have 200, and each cell means whatever the cell we will actually construct, we will actually having the expectation, we need to have the expectation to be greater than or equal to 5. These are just the norms from multiple research. This is actually being stabilized. And then we have say summation over say OI, that's actually observed value, is actually equals to the summation over the expected value. Means whatever the total of the value is, you will actually get the same value from the sum of the expectations. So now, and also we will reject the h naught if, means whatever the null hypothesis is, will reject the particular thing if the xc square is coming out to be greater than the x alpha square as the previous norm. If it's actually greater, you will reject h naught. If it's actually lesser, you will accept the h naught. Now let's actually construct the particular table. So we see that class A, right? So there are the classes, right? Classes are, what are the classes in our case? The classes are actually company A, the company which we are studying, and we are increasing the add of the company B is actually main competitor, and the others which are actually the rest of the competitors in the market of the fabric softeners, right? So now observed I, now there comes the column that is actually observed I. So 102 were observed for the were found to be with the company A as the fabric softener choosers. And then we have the 82, that's actually competitor chooser, and 16 were the other choosers, and total sample size was actually 200, right? Now the market share of the company A is actually 45, the market share of the company B is actually 40%, and the others are actually 15%. How we got 45 is actually what we did, 40 plus 15, that's actually 55, and we subtracted 55 from say 100, so we got the 45, and this is how we know that our company is actually having a market share of say 45. Now the probabilities according to this market share percentage will come out to be say 0.45, 0.4, and 0.15. Just divided that by 100, right? Because the percentage is totaling up to 100. Now we actually get the expectation of I. So whatever the total value is, we will actually multiply with that. So the total value of this frequency is 200. So we will actually multiply this with this probability. That's actually 45. 0.45 multiplied by 200. We got some value. Then we have actually multiply with 0.40. We got some value. Then we actually multiply with 0.15, and we got another value. Now the sum of all the expectation value is coming out to be say 200, and also the sum of all of the values are coming out to be say 200, right, in this particular case, right? Because, well, this is also say significant and very easy to see, because see, all of these will actually add up to 100, and we are actually multiplying with the actual total sum, that's actually 200. So this will in turn add up to 200, because we are actually just getting some percentages from the 200, right? Okay, now you need to calculate the particular c value, right? Okay, so what was the formula of this chi-square value, right? That's actually your OI, right? OI means whatever the observed value is that, and you will subtract from the expected value divided by expected value, and the observed value minus expected square. So this is a particular column, right? And we actually just add up, means we just did that 102 minus whatever this value is, I think 96, right? And then we actually subtracted that and square of those and divide by what, 96, right? And in this fashion we got 1.6. Similar doing with 82, 80 square, so difference square, and divide by 80, we got 0.05, and third is 6.53. We add up all of those, to actually get the chi-square value. That's actually 8.18. Now we actually want a critical, now we have the say two classes, so degree of freedom is actually 1, because 2 minus 1 is actually 1, sorry, 3 classes, so 3 minus 1 is actually 2, so we have 2 degree of freedom. The level of significance is 0.05, so actually got the chi-square critical value to be say 5.99. 8.1 is actually greater than 5.99, so reject h naught, means that it is actually not a good fit for this particular case, and will actually reject h naught, right? So the conclusion is that this particular value, right, this particular null hypothesis was false, and the alternate hypothesis is good, is true, right? That is, fit is good and the objective data is drawn from the population having the specific distributions, right? This is actually false, and the fit is not good is actually the true case, and this is how we'll use the chi-square test for now, for this good fit test, right? Here only we will have different table, otherwise in the previous two cases we have the same table. Thank you so much.